Okay, we'll wrap up chapter 7 today. And so we stopped here with our coupling capacitors and bypass capacitors. And let's go to a DC and AC analysis. So we looked at amplifier circuits, right, at the end of chapter 4, and then we looked at designing a C amplifier. Now, consistently, I stated that we will we set up our BJT or our device to operate in a certain active region, certain point in the active region to function as an amplifier. And that is performed by the DC voltages that we apply. And then on top of the DC voltage, we apply an AC signal, right? That's how it functions as an amplifier. Whether you use it as an amplifier, whether you use it as a electronic switch, AC and DC signals come together inside the BJT. So when you're performing analysis, it helps if we separate out the two analyses, obtain individual results. And so for that, we'll look at how we can do DC analysis and then how we can do AC analysis separately. Okay. So if you think back to chapter 1, where I spoke about notations and subscripts. Remember, uppercase notations indicate DC, lowercase notations indicate AC. If you have a lowercase notation with a uppercase subscript, that means it's AC and DC. Okay. And so if you're performing DC analysis, we would remove all of the AC signals and the capacitors. Excuse me. All right, so we would remove the AC signals. We are not looking at any of the AC portion of the analysis, right? So we remove the AC signal. And then capacitors in DC, once they reach steady state, behave like an open circuit. So if you're applying only VCC, only the biasing voltages, which are DC, then these capacitors have infinite impedance and they behave as open circuits. Okay. Thus, the AC signal is automatically disconnected. The emitter resistor, sorry, not the emitter resistor, the output resistor is also disconnected. And that's it. And that takes us into the circuit that we studied in the 4-resistor bias or the voltage divider bias. And we analyze the circuit as it is and obtain our DC Q points and DC biasing voltages. Okay. So as far as DC goes, it's straightforward. We simply take the capacitors in there, make sure the AC sources are 0, replace all the capacitors with open circuits, and you can analyze the circuit solely for the DC voltages being applied. Yes. Yeah, like so the question being asked is whether these circuits would function better at a particular operating frequency. The answer is yes. But that's a given, that's a point that applies to any circuit. If you wish to, let's say, audio applications, right? Audio applications. And again, going on a bit of a real life example. You have a home theater system, let's say 5 channels and 1 subwoofer, right? all the 5 speakers are very small in size. Subwoofers are pretty big. Why? Because they're reproducing lower frequency signals. They're reproducing lower frequency signals. They have to move a lot of mass, meaning there's a big cone that needs to be moved. Okay, that requires a lot of power. That's one of the things. But the frequencies that go to the subwoofer are typically less than 150 hertz. Okay, so that's where a low frequency amplifier is used. And the design it's a complicated design. So that's one of the reasons why the good subwoofers cost a lot of money. Okay, so the answer to that point or that observation is that every amplifier is designed for a certain frequency range. If you buy it off the shelf, they might say, okay, it works between 20 hertz to 20 kilohertz, like an audio amplifier, right? 20 hertz to 20 kilohertz. But a really well-designed amplifier that accounts for unexpected irregularities in the signal or in the system environment would be more expensive because there'll be a lot of things being added on. Right now, we're just simply looking at a circuit at its most basic level. Okay, so no AC signal being applied. You have coupling and bypass capacitors. We simply replace them with open circuits. And if there are inductors, we replace them with short circuits. EE 211, 211 and 212. So replace all capacitors and all inductors with your steady state or DC steady state equivalents. Mm-hmm. So the question being asked is if the operating frequency is dictated by the capacitor. It's actually the other way around. The application dictates the operating frequency of the circuit, and the operating frequency of the circuit dictates what value of capacitor you would choose. So as an engineer, you would always have a goal in front of you, and what you're doing is trying to reach that goal. So you're working backwards, right? Yes. At DC steady state, doesn't matter what kind of capacitor it is, it's always going to behave like an open circuit because frequency is 0. AC is on the next page. Yeah. So capacitor is open circuit, inductor is short circuit. And this circuit, of course, results in the voltage over bias. So simply analyze for the DC voltages in the circuit. So speaking of AC, if we wish to perform AC analysis, we do the same thing, but we replace all capacitors and inductors with their AC equivalent. AC equivalents. So capacitor behaves like a short circuit. Inductors behave like a open circuit. Now, we are not talking about the frequency range just yet. Again, the point is that if we wished to have a circuit working at a particular operating frequency, then we would choose the value of the capacitor or the inductor so that it would behave as a short or open circuit. Does that make sense to everyone? Right? Yes. So question being asked is if we wish the AC coupling to work, would we want it to what? It's not that we want to, it's that's how it works. That's the fundamentals of a capacitor. So capacitor fundamentals. If you apply a voltage to the two parallel plates, electrons and holes are pulled away. Well, not pulled away. They are pushed towards the two parallel plates, but they cannot actually go through the plates. Again, capacitor fundamentals. Just a quick recap. If you apply DC or AC for that matter, what happens? What happens to the electrons in the wire and the plate? They get pulled towards the positive terminal, leaving behind positive charge. Here, negative charges are repelled. So electrons flow in this direction, accumulates negative charge here. Charges accumulate, hence we get an electric field, hence we get a voltage across that capacitor. They are not actually going through, even though we say that current is flowing through the capacitor, it's not actually flowing through a capacitor, it's just flowing through a circuit. So if you apply AC, what's going to happen? Charge is going to move this way, this way, this way, this way, constantly. Higher the frequency, the faster the movement. So it appears as if electric current is flowing in the circuit. So you apply DC. Once the voltage here reaches the applied DC voltage, let's say this is V, that's when it stops flowing because charge is now balanced on both sides. So electrons stop flowing in the circuit. Capacitor has reached full charge, behaves like an open circuit. So it's not as if for AC it must charge. It is like, because it is charging, that's why we model it as an open and short circuit. Does that make sense? All right, coming back here. What were we saying? Oh yeah, so all the DC supplies and sources are replaced with the equivalent, meaning voltage sources are replaced with all DC sources are replaced, actually are reduced to zero. Reducing a source to zero would mean that you would replace a DC voltage source with what? Anyone? Short circuit. Current source? Open circuit. So in this case, we have VCC here. We replace it with a short circuit, meaning that node at the top is directly connected to ground. Okay, VCC is replaced with a short circuit. Hence it gets connected to ground. Output, of course, stays connected to ground. Capacitor behaves like a short, so it bypasses the emitter resistor. Coupling capacitor behaves like a short circuit. And so it connects the AC input signal going into the base. Okay, going into the base. So far, so good. VCC is a DC voltage source. So it is replaced with a short circuit, which means top node is connected to ground. This alters our circuit. Emitter resistor is bypassed. And AC input signal is being coupled to the base. Now, because it is connected to ground, we can redraw the circuit like this. RC becomes parallel to the output voltage, output resistor 3. So RC and R3 are in parallel. And because again, at the top, we have a short, R1 and R2 are also in parallel. reduce the resistances. And you get the simplified model that is shown here. So now you have 3 resistors to analyze in the circuit. Right now, we are not doing anything to the BJT. So DC analysis was straightforward. There's nothing much. We have the BJT, we have the external circuit. For AC, we have to first modify the external circuitry, which we did. 5 resistors are now reduced to 3. And then at this point, depending on your application, you choose a specific BJT small signal model. So external circuit is reduced. Small signal model. So far, so good. So now that begs the question, what exactly is a small signal model? And what do we mean by small signal? So let's look at small signal analysis first. A diode in reverse bias, we model as an open circuit. Now, assuming it's an ideal diode model or a constant voltage drop model. Reverse bias diode is modeled as a open circuit, meaning a resistance with infinite value or infinite resistance. In the forward bias, it requires a certain voltage drop in order to conduct. So we can model a resistor, we can model a diode as a resistor. That resistor has a value of RD. It drops a voltage across it known as VD. And from Ohm's law, we get diode current ID flowing through that resistor. Okay. So now, if you're analyzing this just for AC, as evident, again, all lowercase subscripts and notations. So this is all AC, right? VD, RD, ID is all AC. If we take any point along the diode characteristic, any single point, we can find the diode resistance at that point by applying Ohm's law. Yes? Right? Even though the device is non-ideal, you can take any point along this diode characteristic and find a resistance for that particular operating point. Right? You have the diode voltage and the diode current at that point. Apply Ohm's law, you find the diode resistance at that point. That would be known as the DC or the static resistance. And then what we will do is we will determine the dynamic or AC resistance by picking the operating point and taking 2 points a little bit further away from that operating point in both directions. So as an example, we have the Q point here, right? We have the Q point there. And you will find 2 other points. Typically, I would say you would take 2 points on either side of the Q point. Doesn't have to be 2 points on either side of the Q point. Typically, that's what I like to do. But any point that's shifting away from the Q point will give you a small value of the change in the voltage and a change in the current. Okay, so this is the original Q point right there. And this is the shift. This is the shift away from the Q point. Okay. So now you have 2 points on that characteristic. You have 2 points on that characteristic. And those points are very close together. So effectively, they are linear. Or not they. The distance between the 2 points is small. So we can say it's the linear portion of the diode characteristic. We are analyzing a small portion of the diode characteristic, hence small signal analysis. Most AC signals that we would apply would be small. Okay. Most AC signals would be small compared to DC voltages and DC currents. Hence the name small signal analysis. Yes. Always in the characteristic. Yes. So the second point. So all the points that we're talking about, they're all lying on the diode characteristic. Remember, I said, right? You can find the DC or static resistance by choosing any number of points on the diode characteristic, right? If you choose any point, let's say above this portion, more likely than not, the diode resistance would be very, very similar. But if you choose something here, then the diode resistance might be different. Yes. So if we apply a very large signal to the diode, would that still work? Yes and no. If you just want a starting point for analysis, then yes, it would work. But if you want an exact number on how it would behave for, let's say, for instance, like a 5 volt or a 10 volt signal, then it may not work. Yes. Yes. This is just random. There's no circuit here. So question being asked is, what circuit did we use? Well, there's no circuit here. There's no circuit. So add to the Q point, it'd be VD ID, right? One single point, so DC or static resistance. AC or dynamic resistance would be given by the change in the voltage and change in the current, which is indicated by the lowercase VD and ID. And so we can write RD. Again, pay attention to the lowercase, right? Uppercase RD would simply be the DC resistance. Lowercase RD would be the AC resistance. For AC resistance, you can take any 2 points. Again, as I said, usually when I start solving, I like to take 2 points on either side of the Q point. So if my diode curve is like this is my original Q point, I would choose a point above and I would choose a point below. And again, depending on where your original Q point lies on the curve, the resistance values would be different. In this case, RD would be the change in voltage divided by the change in current. Ohm's law. And if we take the inverse of RD, meaning the conductance, which is given by the slope of the characteristic GD. So diode resistance is RD, diode conductance is GD. For a forward bias diode, see how much time, 37. For a forward bias diode, we can write GD as the diode current in forward bias plus the saturation current IS over the thermal voltage VT. Just a small derivation. Typically, ID is much, much larger than IS. We can write conductance is approximately equal to diode current, thermal voltage. So if you have a forward bias diode, you're applying a DC voltage and current, find the Q point, you'd have ID from there. And if you have an accurate temperature measurement, you can calculate the thermal voltage at that point. And a close approximation for a diode conductance can be given by this equation. Diode current over the thermal voltage. VT. This is valid for small signal analysis, but small signal in this case would require it to be less than 50 millivolts. So to be considered small signal, VD should be at least less than 2 times the thermal voltage, which is approximately 50 millivolts. So if you want it to be considered linear, good value for VD would be approximately 5 millivolts. Yes. Where? VD should be far less than twice the thermal voltage. That the equation you're referring to? No, we are saying the change. We could apply a 5-volt signal, but if you're looking at the diode characteristic, we can just take a look at the small change. Your input could be anything, but if you're analyzing a circuit for like a small signal, let's say you just want to find the dynamic resistance, then if you wish to apply these linear techniques, then we need to make sure that the data is also linear. And so for the data to be linear, we can just say we'll shift it away by 5 millivolts or less, consider it linear, apply our Ohm's law, and find the resistance that way. And that gives us an approximate value, even if the signal is large. Okay. Even a 5-volt signal or even a 1-volt signal can have infinite values, any kind of AC waveform. And so it's constantly changing value. You can take 1 millivolt steps, you can take 0.1 volt steps, but it's changing, right? So for every change, we can describe the diode resistance. So basically, this will describe how the diode will oppose any change in the input signal. Hybrid pi model. Okay, so that was for the diode. Let's look at the BJT. So the BJT, there were many models. The current one that's used in Gamelpool, Eber's mole model was very popular. There's hybrid pi, which we'll look in the next slide. And here we have a 2-port model for a standard BJT. So if the BJT, and obviously this is the base, collector, and emitter, it's an NPN transistor. We put it inside a box. If you take the BJT, put it inside a box with 2 terminals coming out and 2 terminals going in. We can use a 2-port model to approximately illustrate the functioning of the BJT. Okay. So inside the box, we can represent this as a current source on the input side and a current source on the output side. Right. Just ensure silent. All right. So here we have the inputs, which is the base emitter voltage and the base current, VBE and IB. Here we have the outputs, IC and VCE. All right. On the output side, we can model the output side as a constant current source. Constant current source is dependent on the input. In this case, instead of showing IB, we are showing GMVBE. Okay, because you're using a Y parameter 2-port network. Y parameter 2-port network. Okay. GM, again, G is representing the conductance. So in this case, GM would be the current over voltage, right? Current over voltage. And so let's write equations for all of them. If we break the circuit up, we represent the left side as the input, right side is the output. On the input side, we have GPVCE, sorry, G mu VCE. Output side, we have GMVBE. So both of those are dependent currents, and the dependency is on the voltages on the other side, respectively. I can write IB on the input side is a function of G pi times VBE plus G mu times VCE. On the output side, the collector current can be written as GM VBE minus GO VCE. Excuse me. If a condition exists where VCE is equal to 0, meaning at the Q point, then I can write directly for G pi equation as IB or VBE. I can write GM as IC over VBE. And in the same equations, if I write VBE is equal to 0, then my equations reduce to G mu is IB over VCE. And GO is IC over VCE. It's lowercase. Okay, these are all conductances. So let's look at G pi. G pi, you have the base current. The conductance is describing the ratio of the base current to the base voltage. So this is the input conductance. GM is, what is GM? That would be here. Output voltage and output current. This is output current as a function of the input voltage. So it's a transfer characteristic, hence transconductance. How is it being transferred to the output? Okay. And there is a derivation in the book. I'm not going to go over the derivation right now in class, but we can write that at the Q point, G mu can be 0 because VCE we take it 0. We can write GO as IC over the early voltage VA plus VCE, and GM IC over the thermal voltage VT. Excuse me. G pi can be written as IC over beta O times VT, where beta O is given by the equation 1 minus IC. Don't write it yet. Hold on. 1 over beta F times gamma beta F, partial differential IC at the Q point. There, that's the full equation. This beta O is the small signal current gain. So if you wish, if you bias a transistor at a certain Q point, whether it's in the active region or wherever, Then the beta for the small signal at that Q point can be determined from this equation. So the transistor would have a beta F value, and you can determine the small signal common emitter current gain. Yes. This is the common emitter mode, so common emitter current gain. In your assigned reading, this is section number, what section is this? Should be under chapter 7. So either 7.2, 7.3. Can't remember exactly. But please go through the relevant section and then let me know if you have any questions. So there are, let's see, I got 8 minutes, and it's an analysis for the C amplifier, so I can leave that for Monday, but let's go here. There's a simplified. So this is known as the pi model because it looks like a pie, apparently. I don't know. It looks like this, inverted. And so the modification of the previous model is known as a hybrid pi model. A hybrid pi model. Supposed to look like an inverted pie or something. That's what I've been told, and that's what I've read. And so that's why this simplification of the previous model is known as a hybrid pi model. Okay. So in this case, we are not looking at the input side as a dependent current source. We're getting rid of it. We simply have R pi on the input side, RO, the output resistance, and then IC, dependent current source, as a function of the input voltage. And here, we can write GM is IC over VT. R pi, the input resistance, can be written as O over VT over IC. And RO, output, is 1 over GO, which is the early voltage VA plus VCE over IC. And compared to the early voltage, VCE is far small, and so VA over IC. Yes. Which one? No, these are, yeah. Okay, so the only thing remaining is the small signal analysis of a C amplifier. So we'll use these models and we will apply them to a C amplifier. The one that we looked at for in lab 8 and in chapter 4. And then we can analyze this and determine the gain of that C amplifier. Okay. So we'll end class here today, and I'll see you all on Monday. Friday quiz is beginning at 12 noon until midnight of tomorrow. So you have more than a day and a half. Well, no, actually, exactly a day and a half. Okay. So it's not just till midnight today, it's Friday and Saturday. Okay, Friday and Saturday. And then we'll have a quiz on Monday, the last one of the quarter. And that'll be based on, well, pretty much the last few things that we have done. All right. All right. So Have a good weekend, and I will see you all on Monday. Question being asked is, will this be on the Monday quiz? I haven't yet decided. Maybe, maybe not. If I assign some problems and students can practice some things, then maybe I might have these models on there. Otherwise, I won't. But I will post the announcement sometime later tonight or tomorrow. No, that wasn't our last. No. Yes. The DC analysis, yes. The load line analysis, you mean? So I'm confused.